Hello and welcome. And in this lecture, we are going to learn what is regression and what is simple linear regression. And as we have seen in the class for types of models, regression analysis is a statistical process for estimating the relationship among variables where the predictor is a continuous variable. And here, the focus is on the relationship between the dependent variables and one or more independent variables, or we also call them predictors. So in case of a simple linear regression, there is one independent variable, such as the number of hours of study versus the marks obtained. And it is also one of the very common methods used in machine learning. And in many circumstances, it can also be used to infer the causal relationship between the dependent and the independent variable. Now, typically, when you want to predict a continuous variable, such as predicting the future sale or predicting price of the product or the service, you will use the linear regression. Now, in case of simple linear regression, the equation or function would look something like this, where you have one feature and you are going to predict the value of one dependent variable or feature. Alright, and let's now try to understand what is a simple linear regression in a bit more detail. We have earlier seen this equation as well as such graphs where b0 is the intercept and b1 is the slope of the line. Y is also called as a dependent variable and x is an independent variable. And in case a new data point is added, then we can predict the value of y using the regression line over here. But for that, we need to solve this equation and get the values of b0 and b1. So let's try to solve this equation for an example. So we have this small data set which represents the number of hours of study by a student and the marks he or she has scored. We have also calculated the mean for x and y, and we call hours of study as x and marks obtained, which is also dependent on x, as y. I think it's pretty clear that more you study, there is a higher chance of getting more marks or score in the exam. And when we plot these points on the graph, it looks something like this. And we may have a line passing through these points just like this. And this line will have an equation of y equal to b0 plus b1x. And as we know, b1 is nothing but the slope of the line and is a change in y divided by the change in x. And that is true for all the points on this line. And in case of regression line, when we want to calculate the slope of this line, it is given as sum of the product of the difference of x and y values from their respective means. And then we divide that by the square of the dependent variable's difference from the mean. And this is how it would look. The x bar and y bar are nothing but the mean of x and y. So x minus mean for the first point will be 0 minus 5.38, and the difference of this point from its mean for y will be 66.31 minus 40, which is 26.31. And similarly, we calculate these differences for all the points mentioned over here. If you want, you can pause this video here and compute these values, but this is only for understanding purpose. And then we calculate the square of the x minus x bar and also calculate the product of these two differences. And finally, we do the sum of all of these values. So this one over here, 405.46, is nothing but the numerator of this equation, and 89.08 is the denominator. And when we solve it, the slope of the line or value of b1 will be 4.55. So for this equation, we now have the value of b1. That's great. But we still do not know the intercept or b0. So what do we do? Now let's try to compute the value of b0 so that we have the equation of our line and we can predict future values of marks scored based on the number of hours studied. Alright, so we have x and y axis here, and we have also plotted the mean of x and y. Now, one thing that you need to remember here is that every regression line always passes through the intersection of x and y means, which is nothing but this point over here. So when we substitute the values of x and y for this particular point in this equation, we get 66.31 equal to b0 plus 4.55 into 5.38. And when we solve this equation, we get the value of b0 as 41.8. Great. For now, just understand these points. There is no real reason to calculate at this stage for you. So now, the regression line equation for this example is y equal to 41.8 plus 4.55x, that's the intercept of the line at y-axis, is at y equal to 41.8. And now, using this line and this equation, we can predict the marks scored by any student, provided we know the number of hours he or she has studied. Great. I hope that explains how we can solve the linear regression equation. In the next lecture, we will cover ordinary least square and some more terms related to linear regression. As always, thank you so much for joining me here, and I will see you soon in the next one. Have a great time. Hello and welcome. In the previous lecture, we learned about linear regression, and in that, what is simple linear regression. Also, how to solve the linear regression line equation was also covered. Now, in this lecture, we are going to cover various common terms and one solution method of ordinary least square. Let's first start with the OLS, or ordinary least square. So in this example, we have some data points plotted on independent or x-axis and dependent or y-axis. A regression line, which has an equation as a function of x, is plotted like this. We have seen in the previous lecture how we can draw a simple linear regression line. But for a given value of x, let's say xi, we have an actual value of y as represented by this data point here. And let's call it yi. But if we were to predict the value of y based on the regression line that we have plotted, it would be represented by this data point on the regression line. And this predicted value is called as yi hat. And as you can see from this graph, the two values of y, that is actual and the predicted, have a difference. And they will always have some difference. And this difference is nothing but the prediction error that our model has committed. And similar to that, the majority of the data points will have some error compared to the predicted value of y. In the ordinary least squared method, the model draws a line that has minimum of the sum of squares of the error between the predicted and actual values. So among all the possible lines that can be drawn, we choose the one with the least cost of ordinary square of errors. And the reason we square it is because we don't want to cancel out the positive and negative errors. And now the job of the regressor is to find out the minimum OLS. Alright? And I hope that explains what is the OLS method of drawing a regression line. Even the Microsoft Excel uses this method of regression. Next, let's look at some of the terms that you may encounter in regression analysis. And one of them is the mean absolute error. And as the name suggests, it's the mean or average of the absolute value of the error. So basically, we take the difference between the actual value and the predicted value. And because this difference can be both positive as well as negative, because positive for the data points which are above the regression line and negative for those which are below it. And that's why we take the absolute value of that error. We then do a sum of all of these values and divide it by number of observations. Great. And MEA is used to measure how close the forecasts or predictions are to the eventual outcomes. What that means is lower the value of MEA, better or more accurate are the predictions compared to actuals. Then next, another very commonly used term is RMSE or root mean squared error. And let's try to read and understand it backward. So first, we calculate the error of the predicted and actual values. We then do a square of it. And this also amplifies the large errors. We then do a sum of all the squared errors and divide it by the number of observations to get the mean of it. And finally, we take the square root of this term to arrive at RMSE. And this is one of the very commonly used terms to understand the effectiveness of the numeric predictions. And compared to other measurements, RMSE punishes and amplifies the larger error. And that is because it is squaring and then taking the root. Then the last one from this lecture is the relative absolute error. And as I suggested in the past, try to read these terms backward to understand the meaning of it. So we have the prediction error, we consider the absolute value of the error, and then sum all such errors. Secondly, we also do the sum of the distance of the actual values from the mean. And the ratio of these two values is nothing but the relative absolute error. Great. And with that, we have come to the end of this lecture on OLS and common terms used in regression. In the next lecture, let's build a model for linear regression. And I am, as always, super excited to show it to you. Thanks for joining me here and have a great time. Hello and welcome back. Now in this lecture, we are going to build a linear regression model using the ordinary least square. So here we need to build a model to predict the price of the vehicle or the automobile based on the available historic data. Now this dataset is already provided by Microsoft. So all you need to do is simply search for automobile price and there it is. And let's drag and drop it here. And you won't find this dataset in the resource sections of the lectures because it is already provided by Microsoft. And if you want to download it, then you can use the export data module as we saw earlier. Alright, so as the first step, let's visualize the dataset. Now this dataset has got 205 rows and 26 columns. And it consists of 3 types of data. Now the first type from this make of the car is the specification of an automobile. And that is in terms of various characteristics such as its make, fuel type, length, height, engine type, and so on. Then if you come back to the first column, you will see this symbolic column, which is nothing but the assigned insurance risk rating. Now this rating corresponds to the degree to which the vehicle is more risky than its price indicates. And what I mean by that is the cars are initially assigned a risk factor symbol that is associated with its price. Then if it is more risky or maybe sometimes less, this symbol is either adjusted by moving up or down. And this process is called as symboling. So a value of +3 indicates that the auto is risky and -3 that means it is probably pretty safe. Now if you click on this column, you will see that it has 6 unique values and it actually is a category of symbols. And that's why we should treat it as a categorical variable. So please make a note of that. Then this second column of normalized loss is the relative average loss per vehicle per year. Now this value here has been normalized for all autos within a particular size. And by size, I mean such as 2-door small or sports or normal sedan and so on. But the problem with this column is that it has too many missing values. We have just 205 rows here, and this column has 41 missing values. That's 20%, so it's better to drop it. Now, you may ask why 20% and why not 10%, but there is actually no rule regarding the accepted level of missing data. But I personally prefer to drop a column if it has more than 5% if the dataset is small, or more than 20% if the dataset is big enough. So we won't select this column for our predictions. So make a note of that. And then if you check the columns for missing values, you will find that number of doors, which is right over here, has 2 missing values. Then bore also has 4 missing values. Then stroke also has 4. And if you go down further, you will see that horsepower has 2 missing values, peak RPM has 2, and then the last column of price also has 4 missing values. These are fairly in an acceptable range, so we will keep the column, but we can choose to remove the rows. So you should ideally check them column by column, but just to speed up things, and because I know in advance, I'm mentioning these columns directly. And you can also use summarize data module and get this information. All right. So basically, this tells you that we would need the edit metadata for symboling as well as the string variables to convert them into categorical. And we also need to clean the missing data. So let's go ahead and do these data processing steps in the next lecture. As always, thanks for watching. Welcome back, and let's now proceed and complete this pipeline. So let's bring in the select columns module here because we want to exclude the normalized losses column. And then connect this automobile price data to the input of select columns, and then click on the edit column link. Now, I don't want to select 26 columns here, so what I can do is, and we have not seen this feature of this module earlier, so simply click on all columns, and then we can add another rule by clicking on this plus button, and here we can specify the exclude as well. So choose that from this drop down, and then exclude by column names here, and then specify the normalized losses in this box. All right, save it, and then let's do the next step of cleaning the missing data. So search for it, and then drag and drop it here as always, and then let's connect it to this select columns output. And as you know, we cannot clean 2 types of columns in one operation unless we want to replace them. So you can go ahead and clean the numeric and the string data separately. But for now, I'm going to simply remove those rows which have missing values. And for that, click on this edit column again. And once again, include all columns from this dropdown. Save it. Okay. And now I'm simply going to select from this cleaning mode dropdown the option of remove entire row. So basically, it will remove any row that has a single missing value. I hope this is clear. Then the next step is to make the string columns and the symboling columns as a categorical type. For that, let me bring in the edit metadata module. So simply search for it and then drag and drop it here. Connect the output of clean missing data to the input of this one. Okay. And then click on the edit columns link. Now here, let me first choose the column type from the first dropdown, and then from this type, select the string columns. Great. But now symboling won't be selected as part of the string. So either we can add another condition here, or we can simply click on this radio button of by name, and here you will see all the 10 columns of string type. Let me simply click on this plus button of symboling, and it will also get added to our selection. Great. Save it. And now even the error will be gone. But we are not done here yet. We need to change them to categorical. So click on this drop down by the same name as that, and choose categorical. Great. Leave rest of the values unchanged. We don't want to change their data type, or even don't want to give any new column names also. That's it. Great. And now one last thing we need to do in our data processing step is to split the data for training and testing purpose. So simply bring in the split data module, search it, drag and drop it, and then make the right connections over here. Okay. And then let the splitting mode be by rows, and the training data will once again be 70% or 0.7 over here. Great. I'm going to leave everything else as it is. I'm not changing the stratified split to true because our predicted column is price, which is a numeric variable. So basically, only for classification type of problems, we would be using this stratified split to true. Okay, great. So that basically completes our data processing steps. And in the next lecture, let's go ahead and bring in the linear regression algorithm, train it with this training data, score or test it, and then also see the evaluation of it. As always, it's a pleasure to teach you. Thanks for watching. Welcome back, and let's now bring in our linear regression module and train it. So simply search for linear regression, and then drag and drop it on the canvas. This one, because its algorithm does not take an input, only an untrained model is passed as an output. So let's now see its parameters. And the first one is the solution method. Now, this parameter actually decides how we are going to derive the final equation for linear regression. We know one of the methods to solve linear regression is ordinary least square, or OLS. Then we also have the online gradient descent as another method. So first, let's finish one experiment using the OLS method, and then we will learn about this online gradient as well. Then we also have the L2 regularization weight to avoid overfitting of the data. And finally, this binary value of whether to include the intercept or not. The intercept is nothing but the B0 or the constant value that we have as part of linear regression formula. So this parameter simply tells the algorithm whether to consider the intercept as 0 or not. Okay? And let me provide the random seed as 1, 2, 3. Great. And now let's train this model using the same train model module. So search for train model and bring it in. And now let me connect the untrained model from the linear regression to the first node and the training data to the second node. We have done this numerous times. Now for this train model module, we need to provide the label column or the feature we are trying to predict. So click on edit column. And this is basically our Y. So because we are trying to predict the prices of the automobile, specify the column of price over here. And you can only specify one column. So save it. And then make this model explanations to true. This will simply help us to get various details such as which features were important and their importance score. Great. And then the next step is as always to score or test our model. So get the score model module, bring it in, and let's connect the trained model to it. And then the test data from this split data module, which is just 30%, will go to this another node. Now, as you can see, these steps are pretty straightforward for any supervised learning algorithm that we use here. Whether it is classification, whether it is regression, or within that, doesn't matter what type of algorithm you have, these steps are same. And finally, let's search for evaluate model and get it here on the canvas. Let me simply adjust some of these things. And let's provide the output of the score to evaluate. Perfect. And I hope you are doing it along with me and have completed all these steps. And if you have been doing it, make sure all the connections are right. And also make sure that you have a compute instance created, and also provide that as the default compute for this pipeline. And if all those steps are done, then what are you waiting for? Hit the submit button here. And then let me create a new experiment for now by the name linear regression. Great. And then submit it again. It will start running it, and it may take some time to execute. So let me end this lecture here, and I will see you soon in the next one with the evaluation result. As always, thanks for watching. Welcome back, and wow, our linear regression experiment has run successfully. So let's now evaluate and analyze the results of it. So first, let's go to the score model, preview the data, and then score dataset. So this has got 26 columns, and we removed one column of normalized losses. And if we go to the end, we have this scored label column added. So that's kind of even over here, that's fine. And the scored label here has the predicted prices as per the linear regression model. And if you click on this price column, you will see that it has a range from $5,000 to all the way up to $45,000. Ideally, we should have normalized the data, but that's okay for now as we are just learning. And if you want, you can do the normalization also. Then if you analyze the price versus the scored labels visually, it's not that bad actually. I mean, here you have 9639 versus 10,900. Then for the second one, the actual price was 6377, whereas our model predicted the price as 6010. Which is pretty close, just within a range of 5%. It's pretty much close even for this third record, but for the fourth one, it completely missed it. So you have few hits and few misses, but overall it appears that the predictions are within 10 to 12% range. And this is only to provide you some visual information, but this is not how we need to analyze the entire dataset. Let me close this and then go to the train model module, click on it, and then expand this tab over here. And within that, I want to show you the explanations for this train model. So you may want to click there if it is not already present. And here you can see the aggregate feature importance of all the independent features. And by default, it shows the top 4 features. But you can always move this slider and see as many variables as you want. So as you can see, the engine size is the topmost feature, which means it influences the price of the vehicle the most. Then the second most important factor or the feature is the horsepower. And accordingly, you can go ahead and check them. Now, don't worry about these importance values which are in hundreds and thousands because we have not normalized the data. And that's why you see them like this. In case of normalized data, you will see them below 1. Alright, great. Then if you click on individual feature importance, you will see a graph like this. And it is nothing but the scatter plot that explains the behavior of the individual features. So for checking the individual feature and maybe to see some other graph, let me click on this index first, and then on this radio button of dataset. And from this select feature drop down, let me select the engine size. Click on select, and then on the y-axis, let's select the actual price of the vehicle. And that is nothing but true y, this radio button over here. Click on select, and you can visually see it's pretty much obvious that as the engine size increases, the price of the vehicle increases proportionately. Alright, so as you can see here, how the individual features have played their role. Great. So let me close this. And everything so far that we have seen was great to understand in terms of feature importance. But still, we have not been able to answer how good is our model with one single metric. For that, let's right-click on Evaluate Model and see the evaluation result. Great. So here we see various errors such as mean absolute error, RMSE, relative absolute, and so on. So our RMSE is 2462, but that's just an absolute value. Now, we really cannot say whether it is low or high. So let's look at this relative absolute error, which is 0.38, which is not bad. I mean, ideally, it should be close to 0, and a very bad one is close to 1 or sometimes even greater than 1. So we have not done that bad here, as we have, considering we have less data. Then we are using the model with almost default parameters without many other advanced techniques. So still we are doing good, because our aim here is to understand and learn how the linear regression works. Okay. Then we also have this one metric called the coefficient of determination, which is pretty high, close to 0.87. And that basically means our model has not actually performed that bad. The higher value of this coefficient of determination means that the model performance is good. And higher, the maximum value is 1. So if it is closer to 1, we have done pretty well. So I know, we have not discussed this particular topic so far. So let's understand what this coefficient of determination is in the next lecture. As always, thanks for watching. Hello and welcome. So far, we have seen what is linear regression and its types. We also covered OLS, which is one of the methods to perform regression analysis. And in the previous lecture, we also created a regression model using OLS. But the big question is, how do we know if our model is a good model or the regression explains the variation in the predicted variable with a fair degree? And that is where the R-squared or the coefficient of determination can help. Now, this R-squared explains how much of the variation in Y or the dependent variable, or you can say what percentage of variation in Y is explained by the variation in X, which is our independent variable. So it is kind of the confidence measure and the determination measure that how determined we are or how determined the model is in terms of certain ratio that it explains the behavior in Y compared to the variation in X. And let's try to understand the concept and the formula of R-squared. So let's go back to our previous example where we performed the regression analysis for number of hours of study and the marks obtained by a student. This was the equation, and we also calculated the values of B0 and B1. Now, using this equation, let's try to predict the marks scored for number of hours of study. So what I'm going to do is substitute the values of X from the column of hours studied and compute Y, which is nothing but marks obtained. And as you can see with the first record, the value of Y will be 41.8 plus 4.55 multiplied by 0. And that's why the predicted marks will be 41.8. And we can compute it for all the records, and this is how the table would look like. Alright? Then next thing we need to do is calculate the difference of actual marks scored and the mean, and then do a square of it. And similarly, we will also calculate the difference of predicted marks and the mean. And we will square that as well. And now our table would look something like this once we have computed all the values. And the sum of these columns gives us the two key terms of SST and SSR. SSR is nothing but the sum of squares due to regression, which is the sum of square of the difference between the predicted value and the actual mean. And SST is the total sum of squares, that is sum of square of difference between the actual value and actual mean. And once we have these, the R-squared or coefficient of determination can be calculated as the SSR divided by SST. Now, higher value of R-squared means that the variation in Y is well explained by the variation in X. And it is actually right, because if you look at these terms here, the only change is the actual versus the predicted values of Y. If the predicted value is very close to the actual value, the SSR will be almost same as SST. And that will bring the value of R-squared very close to 1. I hope that clears the concept of R-squared or coefficient of determination. And that brings us to the end of this lecture. And as always, thanks for joining me here. Hello and welcome. And I must say that I'm so excited to cover today's topic. So far, we have covered some basics, then OLS as well as coefficient of determination. And now in this lecture, I'm going to teach a very important and powerful concept of gradient descent. Gradient descent is used while building many machine learning algorithms. And it is the backbone of artificial neural network as well. So before we touch upon the gradient descent, let's try to understand some of the core concepts that will lead us to gradient descent, some of the mathematical concepts. So the first is the calculus, which is at the heart of the gradient descent method, and it forms the backbone of many algorithms. And I know some of you may be feeling a bit jittery with the names of calculus and derivatives. But don't you worry, we will sail it through together. So let's first learn an important concept of rate of change. So we have this equation, y equal to 2x plus 3, and we have also plotted it on the graph like this. So now what we mean by the rate of change is the change in y, or also denoted by delta y, with respect to the corresponding change in x, or also known as delta x. And now if you look at the graph over here, and if we need to find out the change in x and y, we can do that by using the coordinates of these 2 points. So this one is 3 by 9 and this one is 5 by 13. So change in y would be 13 minus 9 and corresponding change in x will be 5 minus 3. Okay? And that gives us the rate of change as 2. So this is also known as the slope of the line. Great. Now let's see another foundational concept of calculus called as limits. So we have this function of y equal to 1 by x. And we know when we plot, it will appear something like this. And here, x can never be 0 because we cannot divide anything by 0. So let's try to see what happens when x is either too large or too small. So as we start increasing the value of x, you will notice that the value of y is decreasing. Let's increase it a bit further and you will see that the value of y has dropped significantly. So we can safely say that as the value of x increases, y will start approaching closer to 0. Or it will be almost 0 when x is infinity. And similarly, if you see here, if we decrease the value of x, you will see that there is exponential rise in the value of y. And as we decrease x further, y becomes larger and larger. So as x approaches 0, y will become almost infinity. Remember, in both these examples, x has not reached those values. And mathematicians love to call this as limits. And it is denoted by this symbol of lim, with a variable shown with the arrow approaching a particular value. And whatever is the result is shown after the equal to sign. So we read this as the limit of function 1 by x as x approaches 0.5 is 2. Similarly, the limit of function 1 by x as x approaches infinity is 0, and so on. Next, we have this equation and its graph plotted on the x and y axis. And if we want to find out the slope between the 2 points on this graph, it's pretty easy. We simply measure the change in y, or also known as delta in y, with respect to the change or delta in x. And we get the slope by dividing the delta y by delta x. That's not a big deal. Now, we have this function, which represents this graph as y equal to x squared plus 10. And let's say we have this second point on this graph. And delta y is, as usual, will be y2 minus y1 over here. And delta x will be x2 minus x1. Now, as you can see on this graph, x1 is basically x. Or we can say x1 is simply x. And because we are moving it by delta x to get x2, what it means is x2 is x plus this small value of delta x. Alright, I hope you don't have any issues until this point. It's pretty neat. Now, based on our function f of x, y2 will be a function of x2 now. So, when we replace x2 by this value of x2, which is x plus delta x, we get the equation for y2 as square of x plus delta x plus 10. Great. And now, when we do a square of two numbers or variables, we can expand it as this. So, over here, we get x squared plus 2 times x multiplied by delta x plus delta x squared plus 10. This is simple maths, and just be with me for some more time. And I'm deliberately going a bit slow here, as you must get this right to understand some of the other advanced concepts of gradient descent. Now, coming back to delta y, which is nothing but y2 minus y1, we then replace the value of y2 with this one over here, and the value of y1 with the x squared plus 10. Because we are subtracting this, the x squared would get cancelled out, 10 will be negated. So for delta y, what we are left with now is 2x multiplied by delta x plus delta x squared. Okay? And as we know from the distributive property rules, we can take the delta x out of this equation and place what is remaining in a bracket in such a way that the overall polynomial equation remains unchanged. So we get delta x multiplied by, in parentheses, 2x plus delta x. And in case you just got surprised by this, I suggest you go back by a minute or so and watch the explanation once again. By now, you must be understanding where I'm going with this. And in case you forgot why we did this, well, we need to calculate the slope of the line, which is delta y divided by delta x, which is nothing but this equation over here divided by delta x. So delta x is again cancelled out, and what we are left with now is 2x plus delta x as the average slope of the line. Great. And once again, congratulations on deriving the formula for the slope of the line to a function. But our job is not over yet. What we now want to get is the slope of the line at a particular point. So this delta is still creating the problem for us, because it still means there are 2 points separated by a distance of delta x. So what will happen if we bring this point closer and closer to x, and so close that delta x starts becoming lesser and lesser and finally becomes almost 0. Now can you guess what is that concept where we can make one of the variables approach a particular value? Did we learn it before? Did I say that at the start of the video? Well, yes, we learned that in limits. Now let's look at this equation again. As we make this point closer and closer to x1, we basically mean it becomes limit of 2x plus delta x with delta x approaching 0. And this is nothing but the first order derivative, or dy by dx. Now as the delta x becomes 0, the dy by dx becomes 2x, or the first order derivative of this function becomes 2x. And as you would know, this is the equation of a straight line that passes through this point. So many congratulations on generating the derivative of this function. This is very, very important to know and understand. So now at this particular point, when x is 4, the slope of the line is 4 multiplied by 2 equals to 8. And when x is minus 4, the slope will be minus 8. So in that case, if our aim is to reach the bottom over here, we now know in which direction to travel depending upon the slope. So if the slope is positive, we travel in this direction towards the left. And if the slope is negative, we travel in this direction towards the right. And finally, when we have a horizontal line with absolutely no change in y, our slope is 0. Great. And I hope so far this is clear. And now with this covered, let's move on to understand the concept of gradient descent. As always, it's a pleasure to teach you. Thank you so much for watching. Welcome back, and let's now try to learn the concept of gradient descent using the concept of derivative that we learned in the previous lecture. So we have this example from one of the previous lectures. This is a sample data set of number of hours of study versus the marks scored by a set of students. So when we plot this data in the two-dimensional space, it looks something like this. Now we can draw a line like this or something like this. But how do we know which one is the best representation of the data? Well, the best line is the one with minimum errors in the predictions, isn't it? And this error is also known as the cost. And we know we can measure the error by various error functions. It can be RMSE or one of those earlier ones, or in many cases, it could be a completely different cost or error function. So let's say we consider the cost function for this linear function as 1 by 2n multiplied by the sum of squares of the errors between actual and predicted values. And here is the number of observations. So let's try to apply the same on our test data set. So let's try this prediction function with multiple values of b0 and b1. So first, let's assume that the value of b0 is 0. And b1 is equal to 1. In that case, our predicted marks for the first observation would be 0 plus 1 multiplied by 0, which is nothing but 0. And similarly, the second predicted value will be 0 plus 1 multiplied by 2, and that's why 2. And when we fill in this entire table, it will look something like this. So basically, the predicted marks takes the same value as the hours of study in this hypothesis. So is that the correct one? Of course not, because we know what are the actual values. So let's calculate our cost or error for this set of parameters. So we calculate the square of the difference of actual and predicted values of y, sum it all up, and then multiply by 1 by 2n. And here was 13. You can pause the video and do this in Excel if you want to try it out yourself. And here the result is 1944.538. So when b0 is 0 and b1 is 1, our cost as per this formula is equal to 1944. So we then do the same for various other values of b1, keeping b0 as 0. And that gives us all the possible values of costs for this parameter range. Here b0 is 0, so we can plot it on a two-dimensional plot. And as you can see, it appears like a parabola. So the cost is very high in the beginning, but it gradually reduces. Then it reaches this bottom and then starts rising again. So the values associated with the parameters determine how your cost or your error function behaves. And now our goal here is to find out a set of parameters that gives us the least possible cost for this hypothesis so that the predicted y is as close to the actual y. So far, we derived this error or cost using only one value of b1. And if we take into account three variables of b0, b1 and error, the graph of b0, b1 and costs would appear something like this when we view it in a three-dimensional space. I actually created this using academio.org, which provides some really beautiful 3D graphs. Alright? So how do we teach our algorithm to descend to the bottom of this structure? Remember, you and me can see the path from anywhere to the bottom in this diagram. But our algorithm is blind. It cannot see. So let's try to behave like a blind algorithm and find out if we can reach the bottom of a physical structure. So for a moment, assume that you need to reach to this beautiful house which is situated at the bottom of the hill. You are either here or over here, and you have been asked to reach the house, but you have been blindfolded and you cannot see a thing. Still, you would be able to start going in the direction of the house, as you know it is at the bottom. and if you follow the descent, you have a chance of reaching there. So you may take this path and reach the house if you are here, or even this one. And if you are here, let's say, then you may take this path and reach the house. But because you are blindfolded, there are high chances that you may cross the house and start going away from it. But very soon you will realize that you are going up the hill, whereas the house is at the bottom. So what do? Well, you turn around and start going down the descent. And you may continue doing that and take smaller steps so that you reach the house which is at the bottom of the hill. The concept of gradient descent is exactly same when we apply it to the algorithms. It takes these steps in the descending order in order to reach the bottom. So how does it do it in pure mathematical terms? Well, let's say we are at this particular point, and we draw a tangent to the curve at this point and identify the slope of it. And this slope is nothing but the gradient or the first order derivative of this function. And we have seen that earlier. So then we take one step in this particular direction, and we can decide the size of the step here as well. And using this step, we assign the new value of b1 calculated as previous b1 minus this step multiplied by the derivative. And by doing this repeatedly for the entire training set, our algorithm can get the set of parameter values which gives us the lowest cost. And how do we know we have reached the lowest cost? Well, the lowest cost is this point over here where our slope or the derivative of this error function is 0. And this alpha or the step is also known as the learning rate. Also, one more thing you must remember is this learning rate acts as a step. And because of that, if your step size is high, there are high chances that you may not reach the actual bottom, as you will always overstep it. And similarly, the step size is very small. It may take a very long time to reach the bottom. And that's why in many cases, the initial step sizes are high. And then as we do multiple iterations, we decrease the step size. And I hope you have paid the necessary attention to this concept because it forms the basis of many algorithms and how they reach the highest accuracy. And the method that we have discussed here is also known as batch gradient descent. And I hope I could make it simple enough for you to understand. In the next lecture, we will cover the stochastic or online gradient descent, which is used in Azure ML's linear regression algorithm. As always, thanks for joining me here and have a great time. Welcome back. So we have already seen how the gradient descent helps us get to the bottom of the error function using the gradient and the learning rate. So basically, we move our parameter value in the opposite direction of the gradient by measuring the error at every such point. But let me ask you a very basic question. How did we calculate the error? We have seen this formula, or maybe some other formula of error, and just in case you wonder why am I asking this? Well, just hang on for a few seconds. In all those formulas, can I ask you what is common? Pause the video if you want and think for a moment. There is something which is absolutely present in every error equation. You can go back and refer to those equations as well. Well, it's the summation of difference of all these predicted and actual values. We may or may not be doing the square of it everywhere, but we are definitely doing the sum of it. Now, let's take, for example, this error function. And let's say we have a training data set with 10,000 records. And that basically means n will be equal to 10,000. Now, let's relook at the steps that we perform whenever we are moving down this graph. So first, we have to read all the records, then predict the value of y as y hat, and then we calculate the error for all the records. Because remember, it's the sum of all the y's, which in our case here is 10,000. And based on this error, we then calculate the future b. So basically, every time we need to recalculate the b, we are going to read all the values from the dataset. And this step of going through all the records and calculating the next value is also known as epoch. Some people may pronounce it as epo and some as epoch. Doesn't matter. Now, let's say it takes us 21 steps to reach this bottom. Then that basically means we would have to read this 5 210,000 times. And what if it is a million record? Then we would be reading it 21 million times. Now, that's not a very efficient way of doing things, and it will take a long time to reach the bottom. And this is also known as batch gradient descent, because we are doing it in batches. And in case you wonder if there is a way of reading only few records as the samples, or a small batch, or just one record, then deriving the error from all these records. Well, of course there is. And that is called as stochastic or online gradient descent. In stochastic, or sometimes it is called as SGD, we read one observation at a time and then calculate the error based on that one observation. And this way, we don't have to read the full file for just one step. But the result that we may get from just one record may deviate too much from each other. And because of that, we also have another method where we take small batches of these observations to calculate the error from one epoch. That way, we can take the advantage of both the faster computation error as well as not getting huge deviations from the individual error. I hope that explains the concepts of gradient and online gradient descent. And now, just to summarize what we have learned here, we first learned the concept of rate of change, limits, and then applied those to understand the derivatives. We then understood how we can minimize the errors by using the derivative or slope of the line along with the learning rate. We then learned the concept of epoch and how the batch gradient descent becomes inefficient for large files. And finally, we learned about the online and mini batch gradient descent. I hope you have enjoyed learning these concepts as much as I enjoyed teaching them to you. As always, it's a pleasure to teach you, and thank you so much for joining me here. Have a great time. Welcome back, and today we are going to see the linear regression using the online gradient descent. So as you can see, I have this pipeline from our previous lecture, and here we use the ordinary least square method, and we know that the second method is online gradient descent. But instead of changing it here, I am simply going to copy and paste this module. So simply right click or copy and maybe Control C or Command plus C. Everything will work over here. Then paste it, great, and let me just adjust it a bit and also hide some of these menu items. Nice, and let me now choose the online gradient descent as the solution method, and straight away we will have the options and parameters changed over here. So let the trainer mode be single parameter, and then if you have paid attention to the previous lectures, you would know what the learning rate is. It's basically the step size for our optimizer. And let's keep it to the default of 0.1. Then by default, the number of training epochs is 10 over here. I'm going to specify 100 for now. And this also means our algorithm will use those many iterations for reaching the bottom. But that also means it's going to take much longer compared to if we had a higher step size and lesser number of epochs. Okay, now in case you have jumped a few videos and you are not getting what I'm saying, then I suggest you go back to the previous couple of videos and things will be absolutely clear. Great. Then we know at a higher level what L2 regularization is. Then this parameter of a normalized feature simply tells our training process that if the features are not normalized, then please do that. That is if we set it to true. So I'm going to leave it to true for now. And next is this decrease learning rate parameter. Now, as you know, if we keep this learning rate too high, there is a danger of overstepping the bottom. At the same time, if we keep it too low, then we may take a huge amount of time and computing resources to reach the bottom. And that's why we keep the initial learning rate as high. So we basically take larger step towards the bottom in the beginning, and then with each iteration or with each epoch, we reduce the learning rate. That way we can get the best of both. Alright, I hope this is clear. So this parameter remains true. Next is the same step of train and score the model. So once again, I'm simply going to select them. Let me change this mouse to selection 2. Okay, and then create a box around it to select these two, copy them, and then paste them. Just move them around to make some space. Great. Now connect the linear regression module to this train model, and then the same training data, which is from this first node of split data module to the second train model. So as you can see, we are basically training them side by side using same training data. Then let's also score or test them using the same test data. So that basically means we need to connect this second node of the split data to the second node of this score model. I hope you're still with me so far. I know some of these arrows could cross each other and it may not look very great. So simply adjust them the way you want. Alright. Then next, we don't have to mention anything for this train model parameters because we copied and pasted the earlier one. So it has the same column name of price. But in case you drag and drop it, you may want to provide them over here. Then for the score model, let it add the score columns. And now, if you remember, I earlier told you that if we need to evaluate two models, we can plug them to these two input nodes of evaluate model module. So simply connect the output of this score model to the second input of evaluate. Great. And we are now ready to submit this pipeline. So click on the submit, make sure the compute resource is created, and then provide the experiment, etc. And then hit the submit button again. By now, you know the process. And this time, when it runs, it will not run all the previous steps. It's simply going to run these new steps of this second branch. I mean, if I can call it a second branch. Okay, so let it run for some time, and I will see you soon in the next lecture with the evaluation result. Thanks for watching and have fun. Welcome back, and I hope you have been able to run this experiment, and it also completed successfully. Now, let's quickly finish this lecture by checking the results. So as always, we can simply right-click on this evaluate result, preview the data and evaluation results. Maximize it, and there we see the different metrics for both the training algorithms. The first one is for OLS-based linear regression, and the second is for our online gradient descent. Now, it has different error values, and in some cases higher, while for RMSE and RSE, it is lower. But our coefficient of determination is slightly better by 0.01, almost 1% you can say. And that's not very significant, I know, but remember, this experiment is with almost default values, and the intention here is to learn what is online gradient descent and how we can run it. Ideally, they say no model is good, but some are useful. So depending upon the type of input data you have, some algorithms tend to perform better than others. So you should try more than one and see which one performs the best. Great. And with that, we have come to the conclusion of linear regression using online gradient descent. And I hope I could explain all the concepts behind it in the simplest possible manner. As always, thanks for joining me here. Hello and welcome. You must have gone through the classic Azure ML Studio by now, as well as the Python crash course that I have created for you. The Classic Studio is pretty easy to work with. It's a very simple drag and drop tool. But it has certain limitations, and the coding, particularly in Python, provides lots of flexibility in doing certain tasks. Now in this section, let me introduce Pandas, which is one of the most powerful packages for data processing. So you have seen the import data module, adding columns, rows, cleaning the missing data, and many other Azure ML Studio modules. And now, when we are working with Python, we can achieve all of these data processing steps using Pandas. So let's go ahead and learn this in the context of the Azure ML Studio. And because you have already learned the Studio, I'm going to compare these data